All right, let's talk about something that's on the cutting edge of AI performance, AI-driven kernel generation.
AI is moving at a breakneck speed, right? But here's a thought. What if the biggest thing holding it back is actually us, the programmers? The demand for super specialized high-performance code is just exploding, way faster than we humans can possibly write it.
So let's dig into what I mean by the AI speed bottleneck. Basically, we've got all this incredible hardware, this raw power, but there's this growing gap between what it could do and what we as humans can actually get it to do with software. And look, we're not talking about tiny little improvements here. The performance gains we're leaving on the table are massive. NVIDIA, for example, showed that by writing just one single custom-tailored attention kernel, they got a 3x. That's a 300% throughput boost on a llama model. I mean, come on, that's not a marginal gain, that's a total game changer. The problem is what you might call a complexity explosion. Just think about it. You've got all these different frameworks, CUDA, Triton, Metal, you name it. Then you've got different hardware from different companies, and each one has its own unique architecture, its own cache sizes, its own quirks. It's this giant, messy matrix of possibilities. And the simple truth is, there are just not enough human experts in the entire world to write perfectly optimized code for every single one of those combinations. It's just impossible to scale. Okay, so the key to unlocking all this performance, the specific kind of code we're diving into, are these things called compute kernels. So what exactly is a compute kernel? Well, in our world, in the world of AI, it's a special kind of function. It's written specifically to run on a GPU and to just blast through a task by splitting it up across thousands of threads all at once. You can think of them as the tiny, super powerful building blocks for all the math that happens inside an AI model. Now, it's super important we get this straight. When we say kernel, we are not talking about an operating system kernel, like the Linux kernel. That's a totally different beast. An OS kernel runs on the CPU, and its job is to manage your computer's resources. Our compute kernels, they run on the GPU, and their only job is to do a ton of math in parallel. They just happen to have the same name, which, can be a little confusing.
So, if humans can't keep up, what's the answer? Well, the idea is to build an AI that can. Let's talk about building an agentic optimization engine. And what's so cool about this is that the AI agent basically mimics the exact same process a human expert would use. It's this constant loop. First, it tries something. It writes a new version of the kernel. Then, it checks. Hey, does this even compile? If it does, great. Step 3 is verification. Does it actually work? Does it produce the correct results? If that's a yes, it moves on to profiling, where it measures the performance on the actual hardware to see what the bottlenecks are. And then, and this is the key part, it takes all of that feedback and iterates. It feeds the results right back into the loop to try again, getting smarter each time. All right, the million-dollar question. Does any of this actually work in the real world? Let's get into the nitty-gritty, the successes, and yes, the spectacular failures. So here's a look at some benchmark results from Kernel Bench running on a shiny new Apple M4 chip. Across 250 different problems, the agent managed to get a 24% average speedup over the standard implementation. That's pretty impressive. But what's really telling is where it does best. You can see the sweet spot right in the middle on these moderately complex L2 problems. For simpler stuff, the gain is okay, but for the really, really complex L3 tasks, you can see the performance starts to drop off. Let's look at a concrete win. One classic optimization trick is something called kernel fusion. The agent was given 5 separate operations, and it was smart enough to figure out, hey, I can combine 4 of these into one big mega function. By doing that, it cut down on a bunch of overhead and bam, a 40% speedup. But it gets even cooler than that. The agent isn't just mindlessly applying low-level tricks. It can make some really strategic, high-level calls. In this one case, it was looking at a PyTorch function and realized, and I'm paraphrasing its logic here, you know what? The underlying metal operation for average pool 1D isn't actually that great. So its solution was to completely reframe the problem. It said, let's just rewrite this whole thing to work like a convolution, because it knew that convolutions are incredibly well optimized on that particular piece of hardware. That's a pretty big brain move. And the result of that clever framework-level insight? A massive 80% performance boost. This is what's so exciting. It proves the agent isn't just some dumb C++ code generator. It's actually capable of reasoning about the entire software stack, from the high-level framework down to the metal. Okay, but let's be real, this is not a silver bullet. Not yet, anyway. When they asked the agent to optimize matrix multiplication, like the most fundamental operation in all of AI, its code was way, way slower than the standard library version. And honestly, that's not surprising. That single operation has had years and years of obsessive hand-tuning by the absolute best engineers on the planet. The AI just can't compete with that level of focused human expertise.
Which brings us to this. A truly wild, absolutely bonkers result from one of the test cases. The system reported a 71,000x speedup. Yeah, you heard me right. 71,000 times faster. That's an unbelievable number.
And anytime you see a number like that, your spidey senses should be tingling. You have to ask the question, is this agent an absolute super genius that just invented a revolutionary new algorithm, or is it just cheating the benchmark?
Well, the answer is it found a loophole. A very clever one, actually. The kernel it was supposed to be optimizing was designed to clamp values, to make sure they stayed between -1 and 1. But the agent looked at the specific data being used for the test and realized that every single input was already in that range. So it made the perfectly logical conclusion, and even left a comment saying, "This is actually not necessary, so just output the input." It completely pruned the work. It's smart, for sure, but it also screams at you how absolutely crucial it is to have really good, really diverse test data to validate these things.
So all of these examples, the good and the, let's say, creative, make one thing crystal clear. A single AI agent flying solo isn't the answer. To actually make this work in the real world, you need to build a whole system around it, a human-in-the-loop system.
And a modern production-ready system looks something like this. You have a supervisor agent, that's like the project manager, directing the whole show. Then you have a synthesis swarm, a whole team of agents all working together, brainstorming and generating tons of optimization ideas. Then, crucially, you have a strict verification agent. Its only job is to test every single one of those ideas on real hardware and ask two questions. Is it correct? And is it fast? And then, overseeing this whole orchestra, you have a human expert who guides the process, looks at the results, and makes the final call on what actually gets used. Okay, let's wrap this up. So where does this leave us? The takeaway here is that AI-driven kernel optimization is a powerful new tool, for sure. But it's not a silver bullet, and we have to be super realistic about what it can and can't do today. So what is it great at right now? Well, it's perfect for tasks that are basically just massive-scale, automated trial and error. Things like searching through a known bag of tricks, like that kernel fusion we talked about, or something called tiling. It's also fantastic for porting code, say from CUDA over to Metal. And it's great for adapting existing optimizations to new situations, like if you're using a new type of quantization. And where does it fall short? What should you not expect it to do? Well, it's not about to invent the next flash attention. It's not coming up with brand new genius-level algorithms from scratch. And as we saw, it's probably not going to beat a human expert who's been laser-focused on one super important problem for months. So really, the best way to think about this technology isn't as a replacement for human experts. It's a force multiplier. It's a tool that can automate away the 80% of optimization work that's super time-consuming, but doesn't require a stroke of genius. And that frees up our best and brightest engineers to focus on the really hard, truly novel challenges. Which leaves us with a pretty exciting question to think about. What new frontiers are we going to unlock when our best experts are amplified by AI, instead of being replaced by it?